All right, so we ended with our 99.9 FM. Okay, and now this is just again a quick reminder that if waves propagate through matter, like an ocean wave propagating through water, that overall displacement, delta displacement of that matter is zero, right? That it might go back and forth, but it'll settle back to that equilibrium point, that where it ends versus where it starts is the same. Okay, so things will move, but then that matter will return. Okay, now let's take a moment here and let's quickly talk through the relationship of these three equations. So we have wave period is wavelength over velocity, okay? And so we have our lambda here for wavelength, our v for velocity, and our time for period. So same thing, right? And we also know that period is equal to 1 over frequency. So how about we take this period and plug it in for period, right? And so that's what I'm kind of showing here is I'm going to take this definition of a period, 1 over frequency, and plug it into that equation. So that's what we end up with. Now, two fractions set equal to each other, one way of looking at this is cross multiplication. So you could say 1 multiplied by speed or velocity is equal to wavelength multiplied by frequency. Okay? And 1 multiplied by anything is itself, right? 5 multiplied by 1 is 5, etc. So 1 multiplied by velocity will just be the velocity. So velocity will equal wavelength times by frequency, or velocity or speed will equal frequency multiplied by wavelength. Okay? So from these two equations, we can derive the third one there. Right now, an important concept, this is going to come up in the exam and on assignments and things like that, is you need to know that in general, sound travels through air at standard temps and pressures of at 343 meters per second. So there will be times when you need to use like this equation or the other period equation where you need to know the speed, and it doesn't directly tell you 343. It says that the sound wave is propagating through air, or that it's a sound wave, right? So here's an example of that. So what is the wavelength of a sound wave traveling through air? So then we can go, oh, well, I know a sound wave traveling through air has a velocity of 343 meters per second with a frequency of 300 hertz. And we want to know what the wavelength is, okay? So again, a really helpful way of setting up any kind of physics problem is write your lists of knowns and unknowns. Then pick your equation, and that equation will be an equation where you know everything that goes in the equation except for your unknown that you're solving for, okay? And so if we're looking back, through these three equations here, I know velocity, I know frequency, and I want to know wavelength. So I'm going to pick an equation where I know velocity, I know frequency, and my only unknown in the equation is what I'm solving for, wavelength. And once you've chosen that equation, then if you need to rearrange the equation to solve for the unknown, we want to get wavelength all by itself. And right now it's multiplied by frequency. So I'll divide both of my equations, both sides of my equation by frequency. And what I end up with is speed divided by frequency equals wavelength. Okay, I'm going to plug that in my calculator. We're going to take speed, which is 343 meters per second, divided by frequency, which is in hertz or inverse seconds. Okay, working with 3 sig figs, so that would be wavelength of 1.14 wavelength units of meters, and we can prove this through a unit analysis. So anytime you've rearranged an equation, you should end with a unit analysis, because it's justification that you rearrange the equation correctly. If anything, you may want to do it before you even plug numbers in, and wasting your time, messing with calculator if you rearranged it incorrectly. We know that wavelength needs to be in meters, and we're taking a speed, which is meters per second, and we're dividing it by frequency, which is hertz, and hertz is the same thing as inverse seconds. So meters per second divided by hertz, which is inverse seconds. And when you divide by a fraction, that's the same as multiplying by the reciprocal. So now we have seconds here on the top and the bottom of this fraction, so those will cancel. So you're left with meters over 1, or meters. So that's our justification that we rearranged this equation correctly. Okay, longitudinal wave and transverse wave. Okay. So in a longitudinal wave, we have compressions and decompressions. And most common one, sound waves, okay? That my vocal cords vibrate, which causes compressions and decompressions, or movement of air, and then that movement of air travels through, that longitudinal wave of those compressions travels through the air and then enters, your eardrum, and then that compression, decompression moves your eardrum, and that sends signals up to your brain. You can hear what I'm saying. And so, likewise, it's your speakers providing that, but if you were in the classroom with me. And so that is a longitudinal wave where we have these compressions and decompressions. Should have brought a slinky with me. Hold on. Let me go and grab one really quick. I'm back. So, got my slinky here. We're gonna look at an example of longitudinal waves. And so it's a compression. It's a compression and a decompression that travels. This might be hard to see because it's so small. So we see so little. We see a compression kind of traveling across there, and then it vibrates back and forth. That one was pretty good. And this compression and decompression areas, as it travels back and forth, that's a longitudinal wave. Transverse wave is different, right? That's where it's going up and down. Ooh, that was a good one for a while there. Oh, there we go. That was a good one. So transverse, different. Transverse, up and down motion. Longitudinal, all within, that one axis. Compression, decomposition. So take a moment in your notes, and I want you to give me a definition for longitudinal and for transverse, if you haven't already done so. Okay. All right, interference. Interference is really interesting. As a wave, propagates through medium, we have crests and we have troughs, right? But what if a second wave is propagating through the same medium and a trough interacts with the crest? Okay, that where one wave was going up, the other wave was going down, and we get that kind of interaction here. So let's see, the crest of one wave overlaps with the crest of another, the crest of one wave overlaps with the trough. So this would be constructive, this is destructive. And so what we're saying here is, like, if we have one wave, I'll make one of them dashed and one of them solid, just so we can kind of like distinguish, I guess, between the two. And we have a second wave coming in through the same medium, and a trough interacts with the crest, and crest interacts with the trough. They are not in phase, they are out of phase, and they end up canceling each other out. Okay? And so that would be destructive interference. And then we have constructive interference, which is the opposite of this, where two crests interact with one another, or you could also say like two troughs interact with one another. If we have two crests, meaning we kind of have our, okay, and then we have our solid one. We have two crests in the same place and two troughs. They're going to add to each other. That this was originally that high, and so now it's much taller, much more shallow. They've combined constructively, and so that would be constructive interference. And in this image here, we see both. We can see constructive and destructive. And so these kind of points where we would get like flat water, kind of harder to identify those, that would be destructive, but where we have these high crests, that would be constructive. Okay, where are we at time-wise? Okay. Oh, nice. Perfect. So that is the end of the notes for today. Okay, guys. Like always, go through, make sure you have all these notes filled out, and then take some time to complete the concept check. So if we shouldn't, fourth quarter, but if we have anyone new to the class, we fill out our notes first, then we complete the concept check. It's a simple quiz based on materials from the notes. And you can take that quiz over and over again as many times as you need, but not until you get 100% on the quiz does the assignment for that day open up. And so it's important that you're taking good active notes. Now, the goal of the concept check is not for you to get frustrated and to just do it over and over again incorrectly. What I want you to do is give it a go a few times, go back and read through your notes. If it's still not making sense, then send me an email. Communicate with me. I want to help you. And then I will happily talk through those questions that you're missing on the concept check. I'll go in on my side and I'll go, oh, it's number 3. And then we'll, talk through that concept so you're able to move on. Okay, so don't get frustrated. Just communicate. I'm here to help you. Okay, guys, this will be an awesome quarter. I'm excited to work with you.